All right, I am, for better or worse, going to talk to y'all about WebAssembly today. You can tell this is a big one because I actually had to print out notes for it. This one might run a tiny bit long, and I apologize for that, but that's why I chose the last slot, and I run the show, so things go my way. So let's get started. First, I got a quick little glossary of a few terms, just for some shared understanding. Some of these are going to come up later, and it's useful to have these defined. First, we've got source code. This is what developers write day in, day out. CSS, JavaScript, Ruby, C, whatever. These are all different types of source code. Compilers are programs that turn source code into bytecode, assembly, or machine code. As an example, GCC and LLVM are C compilers. Javac is a Java compiler. Bytecode is a low-level representation of source code that can be run by other programs. As an example, when you run Ruby, you're not interpreting Ruby. Ruby is compiling your Ruby down into a bytecode and then running that in the Ruby virtual machine. Assembly, or ASM for short, is a lower-level language specific to a particular computer architecture. For example, your phone and laptop likely have different types of CPUs and therefore different assembly languages. And machine code sits below assembly and is a binary representation of that code that can be run directly by the hardware. And if you're lucky, you'll go through your life without having to deal with this. So with that done, let's hop on our time machine and go back to 1995 when I was 3 and Netscape Navigator 2 was brand new software. You may know this as Windows XP Chrome. I apologize for that. It turns out it's hard to get screenshots of 23-year-old software. So this is the first release of a web browser to include JavaScript, which was a new scripting language at the time. It was designed in 10 days by Brendan Eich. It was not designed to be fast. It had no integers. The only number type it has is a double precision float, and it had very few browser APIs. It was run by simple interpreters and pretty slow. By lacking APIs, I meant most of the stuff you're used to as conveniences today didn't exist. Ajax was not a thing until it was added to Firefox in 2000, and even that version didn't work until 2002. But it was useful to add basic interactivity to websites. But if you went back from where we are now to using that, you'd be very sad. But it still worked for adding basic interactivity. It started to be used more and more as time went on. But most developers quickly exhausted the possibilities of the language, and various third-party companies saw an opportunity to provide additional functionality via browser plugins. So this is when you got the rise of ActiveX in Internet Explorer. And as an aside, anyone who missed the old Netscape Navigator animations? I found this while I was looking for this stuff, and I really missed it. But this is a start where things like Java applets start to pop up. They're not really fully integrated into the browser, and they have their own concerns, things like interop and, most importantly, security issues. But this is about the same time we started getting Flash to pop up, with a focus on adding interactivity to websites and animation. It had a number of really bad security issues over the years, but I think overall it evened out. We got some pretty good stuff out of it. So in the meantime, websites kept evolving, and this is one of the things that is a little bit less obvious about the web because there are no versions. Stuff just changes all the time and you don't even notice. So a couple demonstrations of this. So this is what Amazon.com looked like in 1995. When Jeff Bezos was running it out of his garage or whatever. And you could buy books from it. It was nice. And here's what it looks like in 2018. Here's what Google Maps looked like when it first launched in 2004. And if anyone remembers at the time, it was very slow. This was pushing the JavaScript engines at the time to their absolute limits. And here's what Google Maps looks like now. So it's pretty obvious that over time, JavaScript really had to get faster. And eventually it did. Can anyone tell me what this date means? Or why this date's significant? Clark got it. So this is the day that we got the first release of Google Chrome, a new browser from Google. Pull up the old logo, which some of you may have forgotten. And this was the first release of V8 as well, a new JavaScript engine by Google, who had decided that the web was moving too slow for their interests, and they'd like it to be a little bit faster, please. So this was the first browser engine to include just-in-time compilation for JavaScript. And I'm going to give a high-level overview of this because it helps the rest of this, and every chart I found was bad. So the basic version of how this works is your source code is picked up by the browser and run through a baseline compiler. that knows how to compile all of JavaScript, but the end result, it's fast, but it's not super fast. Since JavaScript is a very dynamic language, it can't interpret everything you're going to want to do. Everything can change. Objects can have new properties added. You can call functions with it, whatever the heck you want, things like that. So then it starts running it in an interpreter, along with some monitoring packages assigned, and it starts profiling the code as it runs. And if the JavaScript interpreter sees the same function being called with the same arguments over and over and over, or if it sees you have a loop that's running the same code at the same time with the same types of arguments, it classifies this as being hot code, so hot, warm, and cold code. And if it sees some hot code, it'll send it off to the optimizing compiler if it thinks it's worth it. And the optimizing compiler does not know all of JavaScript, but it knows how to compile a subset of JavaScript with additional type information and make it really, really fast. JIT compilation can actually be significantly faster than native code in some circumstances. It's part of the reason Java is actually really fast. So to send that off, get the result and hot swap it in with the code that is already running in your browser. So this happens if you have, say, a function that takes two numbers that don't look like floating points, they don't have anything after 0. It will do this sort of optimization. The problem is there's also de-optimization. So if you call a function 10,000 times with numbers and then call it with a string, it no longer satisfies the invariance of the compiled code. It has to throw it out and start using the de-optimized version again. And this is fine, and most JavaScript engines actually take advantage of this now. Fun fact, actually, V8 in Chrome until recently, and Safari still, don't actually have JavaScript interpreters. They compile your JavaScript directly down to machine code from the jump. The reason Chrome stopped doing this last year is they found it too difficult to keep up with the rate at which JavaScript features are coming out, because a large part of V8 is implemented directly in assembly. So all modern JavaScript engines take advantage of this, and we're going to take a quick tour through those because some may find it interesting. So Chrome is still using V8 to this date. It's got a bunch of subsystems that have fun names like Crankshaft Ignition and Turbofan because they like being clever. Firefox still runs on SpiderMonkey, which is the same name of the JS engine that ran in Netscape Navigator back in '95. This has seen a lot of evolution through the years, but fundamentally it's still the same engine, ship a Theseus situation. Microsoft Edge and some newer versions of IE run the Chakra engine, and Safari likes to rename their stuff every few years, but the current versions of things are Nitro as the base engine and FTL as their just-in-time compiler. And these are all in general pretty fast. But let's go back to this chart for a second. So we have a baseline compiler that knows all of JavaScript but can't make it fast. And we've got this optimized compiler that knows how to optimize a subset of JavaScript and make it really fast. So what if we make the entire airplane out of the bits that the black box is made out of? Wouldn't that be pretty quick? So Firefox and Mozilla started thinking about this, and in 2013 they announced this fun little thing called asm.js, which they classify as an extraordinarily optimizable low-level subset of JavaScript. And that's basically all it is. It's just a subset of JavaScript that compilers know how to optimize really, really well. It has a few features. It aims to have type consistency. Functions will only be called with the same types of arguments. If you define a function, it's only going to be called with numbers. It's never going to be called with anything else. Type annotations to let the engine make more assumptions about things. For example, you can hint to it that, hey, this is always going to be an integer, or this is always going to be a float. Manual memory management, so you lay out everything as an array and only access it via indices. This lets it pack everything together in memory and makes things faster. And as a side effect of all of these, you see decreased garbage collection usage. You don't have things like strings, so everything can be, you don't have any box values that need to be tracked and thrown around everywhere. If it's just numbers, things get pretty fast. But fundamentally, it is just JavaScript, just less of it. I got a few examples to show what this looks like. So an example, here's a function to add two numbers in JavaScript, takes an x, y, and adds them. And this is what that looked like in ASM. Since JavaScript doesn't have actual type annotations, we have to bolt them on. And in this case, we do this by taking our two arguments and binary ORing them with 0. And what this does is informs the compiler that this is not going to be a floating point number, it's always going to be an integer. And now it can assume that this is always going to be an integer. And this function, in fact, I got a misnamed variable, but this will end up compiled down to a single machine instruction, a single CPU add. Another example is compiling some C++ code and translating it. This takes a pointer to a string, calculates its length, and returns it. And in ASM, we have to do the same binary ORing a couple things. And the mem8 in the middle is that linear memory I mentioned that you have access to. So you take a pointer into it, you make sure it's an integer, you do stuff with it, and you do the same thing in return values. And that's fine, but and this is actually pretty performant. When you run this through a JIT fast enough, you can see performance in the ballpark of 1.5 times native, so 56% of native performance. And in some cases, code for this can be faster than native code because JITs can make more assumptions and have more information at runtime. But importantly, if you're doing some optimizations for this, like Firefox does, you can run this through the optimizing compiler from the jump. You don't need to go through all the other stuff first. And this ends up being pretty fast, but writing this by hand would be a gigantic pain in the ass. Thankfully, we're developers and we have tools to automate this. So we got a tool created shortly after that called mscripten, which is a LLVM, the JavaScript compiler. You may have seen me mention LLVM earlier. I'm going to give a quick overview of this now. So a quick detour on how LLVM is structured. So this is kind of how a normal compiler works. And if any of you have taken a comp sci degree, you may have seen a diagram like this. Raise your hand if you have. So this is what LLVM looks like. You only take care of the bits at the front, which is turning something into a representation LLVM understands. You pass it to it, it does a bunch of optimizations and spits out your machine code. But you can also bolt on a backend to that. So for example, there's a backend for ARM architecture. There's a backend for x86. So we can swap on our own in there. And specifically, we're going to pop mscripten on there because that's what it does. So you take your C, C++, Rust source, run it through Clang, which is LLVM's compiler. It gives the intermediate representation that's been optimized to mscripten, and it spits out JavaScript or asm.js. So basically, C code plus magic gives you JavaScript. And there's a fun quote I like from Gary Bernhardt's talk, The Birth and Death of JavaScript, which is also from 2014, and I highly advise watching this. But one of the points to make is once you have a C compiler, you can compile any C code. And pretty much everything is written in C once you go down far enough. I got a few examples of this. What's Ruby written in?
C. Wow, MRI.
We're not talking about Ruby news here. So someone has compiled mruby into JavaScript. And we have Ruby running in JavaScript on the web. I can define methods. This is IRB. Ta-da, it's Ruby running in JS. What's SQLite written in? C. And someone has indeed compiled SQLite down to a JavaScript file. Clicking this loads it, so it's going to take a little bit. It's a little big, but once it's here, you can just do stuff with it. You wouldn't want to serve this. It's like 3 megabytes of JavaScript. It's insanity. But the point is that you can do it. And once we do this, we can see things start getting a bit faster. Last one, and this is a fun question. What's Windows written in?
C++.
C. So you can run Windows 95 in your browser. Someone has gone and compiled DOSBox and Windows 95. It's read-only, so you can't actually do anything. But you can run Windows 95 in your browser. It's kind of fun. I'm not going to run this because they have a few, well, it takes a while to load, and they got some flags like, are you really sure, like legal ramifications. It's like 40-something megabytes to download, but it's all of Windows 95. You can just run it. So this is fun.
It's become a space commander.
Like you want all the vulnerabilities
Yes.
of Windows 95 alongside the web all together.
Yeah, but where do they get the source for it?
That's why they have all the copyright warnings. So let's get on to WebAssembly. So WebAssembly, or WASM, is a new portable, size, and load time efficient format suitable for compilation to the web. An important caveat to asm.js is this is just something Mozilla was working on. This is not something they were collaborating with everyone. They said, here's the thing we've made. If you want to implement optimizations for it, that's fine. If you don't, your optimizing JIT compiler will take advantage of making it fast. So Firefox is a little bit faster at ASM than everything else, but everything else is still really fast. So its goals at a high level are to be fast, efficient, and portable. It's to create an agreed-upon, low-level, cross-platform instruction set architecture. So I mentioned earlier we had assembly. Imagine a shared assembly you can run on any OS through an abstraction layer. It's something that everyone can agree upon. It uses common hardware capabilities. Everything has 32-bit numbers, for instance, to run stuff at native or near native speed. It is intended to be readable and debuggable with existing sandboxing tools. It's actually defined in such a way that browsers typically now implement it just on top of their existing JavaScript engines. They just compile it down to the same bytecode or whatever they're already using. It was also intended to serve as a low-level compile target for C and C++. And the reason for all of this abstractions, by the way, is because JavaScript is good. It's still not fast enough for some things. Like you wouldn't want to run a full-blown like Lightroom in the browser, a Adobe Premiere in the browser. But if you have the kind of speed that you're able to get with these sort of tools, that becomes more feasible as time goes on. Again, it's still downloading X megabytes of JavaScript, but we can improve on that. And since it's part of the web platform, the intention is to add features over time in backwards compatible ways. When JavaScript gets new features, it doesn't break existing JavaScript. When CSS gets new features, your old CSS still works, for the most part, barring things like Flexbox experiments. And most importantly, don't break the web. And most importantly, this is not a replacement for JavaScript. It's a complement. It's particularly useful for things like libraries. As an example, React could replace their core reconciler with one that's written in WebAssembly and get performance boosts. And clients just don't care about that. The only caveat is you need to run in a browser that supports this. And another fun fact, because they're based on a lot of the same ideas, you can actually compile one-to-one WebAssembly to as in JS and vice versa. It's really wild. It's actually already used in the wild in some NPM modules. I linked a blog post a little while ago about how Mozilla rewrote the source map NPM package with it for speed. Some example from the JavaScript side of things. You need to get the data in the browser somehow, and it is binary. So the way you can typically do it now is you just fetch it, take advantage of fetch, turn it into an array of bytes, feed it into the WebAssembly.instantiate method, which your browser now has, and it will compile it, make a new instance of the module that it has, and then give you the result. So here we went through that, and at the end we have an instance that we can call functions on. So it's got two formats, a binary format, which is intended for compact distribution. The extension is .wasm. It's designed for computers. It's optimized for both how fast it can be parsed and file size. It's on average about 10 to 20% smaller than minified and gzip JavaScript. And it can be parsed over an order of magnitude faster than JavaScript. About 20 times faster in a lot of tests I've seen. And in some stuff I've done, it can go even faster. You can also parse and compile functions in parallel, and it can be compiled as it's downloaded. I don't have any examples of this, but it's really fun to check out. And you can actually compile it faster than it can download in a lot of cases. Part of the reason we kind of frown on adding, say, 50 kilobytes of JavaScript to a page versus a 50 kilobyte image is images can be downloaded, and we do all that stuff in the background. JavaScript can't. You have to pull it down in the main thread, parse it, do all that stuff before you can keep going. WebAssembly you can do all that stuff in the background and fully asynchronously. And there's also a text format with .wat is the extension, which may be my favorite thing about the spec. It's a text format useful for debugging, testing, and optimizing. You can actually hand write it if you want. It's not as difficult as assembly. I'll show you some examples in a moment, but it's entirely reasonable. And it's represented as an abstract syntax tree in S expressions. If you've written Lisp or have any sort of experience with ASDs, you should be able to recognize it. And this maps one-to-one to the binary format, so you can convert back and forth all day and you'll have the same result. It only has a handful of types. You got 4 types of numbers. You got 32-bit integers, 64-bit integers, and both types of floats. That's it. The rationale for this is that you can build anything more complicated out of these, and these are very, very fast. CPUs are optimized to work on these things. So I've got a quick example and then a fun little demo. So for example, we're using a Rust function, since that's a language I've been working with a lot lately, that adds 2 numbers and returns results. The no mangle pragma at the top there is just so when we're optimizing, we don't obfuscate the add name like Uglify.js will with JS functions. This is just so we have the same symbol in the final result to call. So we can compile this to WebAssembly either through Emscripten or more directly. If you're curious what I mean by that, ask me later. Yeah. So if we convert this into the binary format and print it out with hex dump, we see some stuff. But on the right-hand side, you can see we got some symbols there. ASM, because it's WebAssembly. Memory, which is part of every WebAssembly module. And we've got our add symbol in there. So it definitely is in there. And if we pop this over into the text format, it looks kind of Lispy. We got some types. We got a function that gets two locals and adds them. It's got some memory stuff, and then at the bottom we have two exports for memory and our add function. Not too exciting. But let's take a quick look at a demo, because this I think is pretty interesting to see how easy it is to get started with this. And it should be pointed out this is all still really in its infancy. Like, we haven't really even begun to make good tooling for this, or even to try and make it fast. And it already is significantly faster than ASM.js. In the ballpark of, like, in some cases, half to 20% slower than native. So I got a demo here. I'm going to pop up an index.html. I'm just doing this super bare bones. Do script.js. Script.js, and we're going to import, let's do something different. So fib from Fibonacci. See, the problem is I've now made myself spell Fibonacci right repeatedly. And we're going to alert fib, and we'll call it with the 31st Fibonacci number. Now we're going to write Fibonacci.rs. No mangle again. And a public function called fib that takes a number. That's a 32-bit integer. We're going to return a 32-bit integer. Oops. Use our pattern matching. And if it's 0, this keyboard tried to type on. At 0 or 1, we're going to return a 1. Otherwise, we are going to return the result of fib with n-1 plus fib with n-2. Not too much right how about. And we're going to use parser, which recently added support. I also linked that. Using some of the tooling in the backend. So just parcel index.html. This might break because I haven't tested this and I'm live coding, and it builds. So we're going to go open this. Mistake not local. 1, 2, 3, 4. And we get an alert with a 31st Fibonacci number. That's it. And I'm going to build this in production mode because otherwise there's a lot of extra stuff. Similarly to JavaScript, if you're not running in production mode, there's a lot of like boilerplate baked in. But if you open up a build directory, there's some stuff in here. Sorry, lsdist. Yeah, I got some stuff in here. So there's some tools provided by a repo I'll link at the end of this that let you convert between the two formats. So I can convert a WASM binary to a .what text file, dist 6, just whatever .wasm. And that's it. There's our function. If you're at all, have you ever read assembly, you can kind of see the shape of this. At the top, we describe our function type, takes a number, returns a number. And there's some stuff in here with loops as it gets compiled, but that's all of it. And you can go back and forth all day. That's it. That's what I got. For more information, I recommend checking out webassembly.org. And the link below that is to the WebAssembly binary toolkit, which has some of the tools I mentioned.
So, given that Brennan and Ike wanted JavaScript to be a Lisp in the first place, have we now come full circle and we've snuck a Lisp into our browsers?
The reason for it to both be a syntax tree representation and as expressions is to minimize byte shedding because developers.
Best
syntax. Yeah.
I have 2 questions.
Shoot.
Sorry, I have 1 question and 1 comment.
Shoot.
Comment is I want every command I run to be Also, what was the parcel thing? I kind of missed
So
that.
Parcel isn't a new JavaScript bundler similar to Webpack. It's
Okay.
focusing on build speed and ease of adding new tooling. I think I can pull up a quick example. I was actually kind of curious how they added WebAssembly support. And Parcel WebAssembly. Basically, they have a concept of assets, and you define a class that knows how to handle that asset with common lifecycle events, similar-ish to React or Backbone. Yeah, sure, also sprockets, but we don't care about sprockets anymore. So go in. Oh no, this isn't the actual. This is an issue asking for it. Gotta love Medium, very fast.
Not in web.
Yeah. All right, well, I can't find it. Go ask me later.
Yeah,
I can show you. It's a fun class, and you can just see how it all builds, and it's really simple.
Yeah.
All right, well, thanks, everyone.
Cool. What browser support it? Like
Everything.
everything?
Everything Evergreen does. The idea being they have an MVP everyone can agree upon, and there's proposals to move it forward from here. As an example, there's currently proposals to add SIMD support for doing a lot of weird things with floating point numbers in parallel. And there's also a proposal to add threads similar to p-threads if you've written a lot of C. But this is all being developed out in the open. You can go check it out. Overview. Oh, that is the overview. I probably don't want the actual specification. It's probably a nightmare. But another note, there is nothing web specific about this. You could.
Except the name.
Sure. Nothing about the specification is specific to the web, and I think they intend to continue on that path. So there's nothing stopping you from writing something that can run it on just bare hardware.